Hello, my name is Ira Bell, and I am an astronomical and planetary sciences student at Arizona State University's School of Earth and Space Exploration. In this lecture, I will be discussing a distant active supermassive black hole known as CEERS 1019. This black hole is located over 13 billion light years away, making it one of the most distant black holes we've discovered. In fact, it was formed just 570 million years after the Big Bang. Before we focus on CEERS 1019, it probably makes sense to spend a little time on the fundamentals. By definition, a black hole is a region of space-time where gravity is so intense that not even light can escape. At the center lies what we call the singularity. Surrounding the singularity is the event horizon, which is often called the point of no return. We can mathematically define the event horizon using the Schwarzschild radius, which is derived from the Schwarzschild solution to Einstein's field equations. Here we have the radius equals 2 times gravity times mass divided by the speed of light squared. This tells us the size of the event horizon for a given mass. For example, a black hole with the mass of the Sun would have a Schwarzschild radius of about 3 kilometers. Supermassive black holes can have a radius of millions of kilometers. In terms of types of black holes, there are a few to mention. Stellar mass black holes are formed from collapsing stars. Intermediate black holes are less understood and harder to detect. Supermassive black holes have masses that are in the millions or billions of solar masses. In fact, we have a supermassive black hole in the center of the Milky Way. So you might be wondering how we find black holes or how we might observe them. Well, we can't see them directly, but we can detect them through indirect effects like gravitational interactions with stars, X-ray emissions from matter falling in, or through gravitational lensing, which essentially causes the warping of space-time. Supermassive black holes reside at the centers of most, if not all, galaxies. At the center of our Milky Way, Sagittarius A star is about 4 million solar masses. Supermassive black holes really play a big part in galactic dynamics. We see them pulling in surrounding gas, forming hot, luminous accretion disks, which releases a tremendous amount of energy. This process can power active galactic nuclei and quasars, which are some of the brightest objects in the universe. What's somewhat surprising is that we're now finding supermassive black holes when the universe was less than 5% of its current age, as I'll discuss shortly. So we're sort of trying to work through how some of these black holes formed and grew so fast early on. The discovery of the distant supermassive black hole, CEERS 1019, was made possible by the James Webb Space Telescope, which has been a complete game changer with respect to our ability to study the early universe. JWST is able to operate in the infrared, which is essential for seeing high redshift galaxies. These are galaxies where their light has been stretched by cosmic expansion to the longer and redder wavelengths. Two of the JWST instruments worth noting here are the NIRCam, which stands for Near Infrared Camera. This instrument allows for taking high-resolution images across multiple bands, and the NIR-SPEC, which stands for Near Infrared Spectrograph. This lets us observe emission lines to measure redshifts and determine the chemical composition of early galaxies. With these instruments, we are able to build spectral energy distributions, spot the Lyman alpha break, and detect emission lines like O3 and H beta to determine a galaxy's age and star formation. In the image shown here, you can see CEERS 1019 in the field, which turned out to be an active supermassive black hole in a galaxy just 570 million years after the Big Bang. CEERS 1019 sits at a redshift of Z equals 8.679, which means that the light we see from it left about 13.2 billion years ago. CEERS 1019 is part of a galaxy with a stellar mass of about 10 to the 9.5 solar masses and is forming stars at a rate of about 30 solar masses per year. In terms of UV magnitude, the galaxy is at minus 18.7, which is relatively bright for the early universe. Its blue spectral scope is beta minus 1.76, which tells us it has somewhat lower dust and younger, hotter stars. Using spectroscopy, the redshift was confirmed with the detection of the O3 5008 angstrom emission line, among others. CEERS 1019 is extraordinary not only because it's so distant, but because it's hosting an active supermassive black hole, meaning it's currently accreting gas and shining brightly as an active galactic nuclei. The energy we see comes from mass-to-energy conversion via accretion. Essentially, the gas spirals into the black hole, it gets heated up, and then radiates right before crossing the event horizon. We are able to estimate the rate at which a black hole is feeding itself by using the equation L equals eta times m dot times the speed of light squared, where L is the luminosity, n is the radiative efficiency, typically about 0.1, and m dot is the accretion rate. If we assume that CEERS 1019 is accreting near the Eddington limit, where radiation pressure balances gravity, then we can use the following equation. L sub ed for the Eddington luminosity equals 4 pi g for the gravitational constant times m for the mass of the black hole times m sub p for the proton mass times c for the speed of light, all divided by sigma sub t, which is the Thomson scattering cross-section. If we plug a black hole mass of 9 times 10 to the 6 solar masses, we estimate L ed at approximately 1.1 times 10 to the 45th watts. In terms of the accretion rate, which is represented by m dot, we see approximately 1.45 solar masses per year. Redshift comes up a lot in astrophysics and cosmology. Redshift tells us how much the light from a galaxy has been stretched by the expansion of the universe. Here we have the equation 1 plus z equals lambda observed divided by lambda emitted. For CEERS 1019, emission lines like O3 at 0.5008 micrometers were observed around 4.85735 micrometers. If we do a quick calculation here using observed and emitted wavelengths, you'd get a z equals 8.679 and several more figures, which is precisely what the team reported. But what does that mean in terms of cosmic time? If we use a simplified equation for a matter-dominated universe, we have time as a function of redshift, t of z, is approximately equal to 2 divided by 3 h naught multiplied by 1 plus z to the negative 3 halves. If we plug in a Hubble constant value of 70 kilometers a second, we find that the results are quite close to being in alignment with the argument that the light from CEERS 1019 began traveling to us approximately 13.2 billion years ago, when the universe was only about 570 million years old. And that's how we confirm that CEERS 1019 is one of the earliest known active galaxies. What further data might be able to confirm that CEERS 1019 is at redshift z equals 8.679? JWST's NIR spec, medium resolution spectrograph, captured a clear and high confidence detection of several emission lines. The strongest here was O3 lambda 5008, observed at nearly 4.85 microns. We also see O3 lambda 4960 supporting the redshift confirmation. In the plot here, you can see both the 2D spectrum and the extracted 1D spectrum. The vertical dashed lines mark the detected emission lines, and the continuum drop near 1.3 micrometers shows the Lyman alpha break, which is caused by the neutral intergalactic medium. This helps confirm 3 things. The galaxy is in fact at redshift z equals 8.679. It is actively forming stars. Strong Balmer lines also support this. The presence of oxygen lines suggests metal enrichment, indicating this galaxy isn't made of pristine gas. There was at least one earlier generation of stars. These observations give us not just a redshift, but also a bit of insight into the chemical state, ionization, and dynamics of CEERS 1019. So why is this so interesting? The short answer here is that scientists weren't expecting to find black holes like this so early in the formation of the universe. CEERS 1019 hosts a black hole that is nearly 630 million solar masses, just 570 million years after the Big Bang. Based on the physics we understand, that kind of mass growth requires rapid formation of seed black holes, possibly from population 3 stars or even direct gas collapse. Also, sustained accretion at or above the Eddington limit for hundreds of millions of years, which is hard to achieve in a chaotic early universe. The discovery implies that supermassive black holes were already common and may have formed alongside the earliest galaxies. In this lecture, we've used general relativity to calculate the Schwarzschild radius of the black hole. We've used the physics of radiative efficiency and mass-energy conversion to calculate how quickly it must be accreting gas. The Eddington limit gives us a natural ceiling for how luminous a black hole can be before radiation pushes gas away. From CEERS 1019's mass, we estimated Led at approximately 1.1 times 10 to the 45 watts, and derived a feeding rate of about 1.45 solar masses per year. We also used cosmology to approximate that a redshift of 8.679 corresponds to just 570 million years after the Big Bang, and we used spectroscopy to measure that redshift based on how emission lines like O3 were shifted into the infrared. This single galaxy gives us a testbed for general relativity, thermodynamics, radiative processes, spectroscopy, and cosmology all wrapped into one observation.